We're going to finish up today dealing with log and exponential equations. We'll look at a few different scenarios that I've come across trying to solve a log or exponential equation. Your main tools, of course, are the law of logs. Log of A plus log of B equals log of AB, and log of A minus log of B equals log of A divided by B, and log of A to the power of B is just B times the log of A. That is, I can take this exponent and move it over. With numbers, that's easy. With variables, it can get a little frightening, so you have to be brave about these things and just kind of proceed as if things will all work out in the end. They usually do. All right, let's take a look at an example. Log of x squared plus 1 equals log of x minus 2 plus log of x plus 3. Someone in the back row, see if you can turn on the lights in the front. I think you just click the switches. Thank you. Very much thank you. So, okay, we can apply our law here, law of logs. This is x squared plus 1 equals the log of x minus 2 times x plus 3. And here, again, we can use either approach. We can either use the fact that we know the log is a one-to-one function. Therefore, these two expressions being equal implies x squared plus 1 equals x minus 2 times x plus 3. Or if you prefer, you could raise each of these to whatever base we happen to be using here. I didn't specify in this problem, but it doesn't matter. And you get the same result because you're taking a function and then applying the inverse function. So you just get what you started with back. Okay, this is a pretty straightforward algebra. Let's do this quickly. This is x squared plus 3 minus 2x, so plus x minus 6. I can cancel the x squareds. I can add 6 to both sides, and I'll get x equals 7. So I have a preliminary solution, x equals 7. But I want to check. I want to make sure nothing went wrong in the whole process. So let's plug it in. We get the log of 49 plus 1, the log of 50, equal to the log of 7 minus 2, 5, plus the log of 7 plus 3. Okay. Well, at this point, we know it worked, because the log of 5 plus the log of 10 is the log of 50. All right. It's good to keep in mind that this transformation here, I have, say, the natural log of x equal to 8. I can always rewrite that not as an exponential, but not as a log statement, but as an exponential statement. The base here is e, the exponent is 8, and here's my x. I can also take an intermediate step, raise both sides to as powers of e, but e raised to the log, natural log of x, that's applying a function and its inverse. So that's, of course, just x, and I get the same thing. Here's an example of the same problem, only in a manner that looks a little scarier. Log to the base 2 of 25 minus x equals 3. Well, okay. Rewriting this again as an exponential. What's my base here? 2. What's the exponent? 3. And that's just equal to 25 minus x. Well, 2 cubed is just 8. If I subtract 8 from both sides, I'm going to get 17. And if I add x to both sides, I'm going to see the solution is 17. I do want to check that, though, as I said. Plugging it in to the original equation, I see log to the base 2 of 25 minus 17 is supposed to equal 3. That's the log to the base 2 of 8. Make a mistake? But that's clearly a true statement, right? The log to the base 2 of 8 is 3. All right. One thing you might see in an equation like this is you might see a little embellishment that shouldn't throw you, because it's just the kind of things we do all the time when we're solving equations. You might see something like this: 4 plus 3 times the log to the base 10 of 2x equals 16. Well, remember, don't panic. What do we know how to do here? Clearly, we want to subtract 4 from both sides. We do with an algebraic equation. 3 log to the base 10 of 2x equals 12. We divide by 3, and we get log to the base 10 of 2x equals 4. And again, now I can write this as an exponential statement, right? 10 to the 4th equals 2x. 10 to the 4th is 10,000. So we just have x equals 5,000. Again, we do want to plug this back in and check. 5,000 times 2 is 10,000. Log to the base 10 of 10,000 is 4. 4 times 3 is 12, plus 4 is 16. So we know that worked. Okay. Questions? And anyone have any problems with the homework? Any specific problems on the homework? We have a couple more to go through, but I think I can, but I think only if you tell me the problem. Thank you.
Plus or e to 2x.
Equals e to the 2x?
No, e to the 2x. That's good. Yeah, 2x minus 21
Minus 21.
equals 0.
Have a clear slate here. Well, I remember on Friday I talked about how, a lot of obvious things one might try aren't going to work. We could try to find the log of this, or raise this to some power, but it's just going to get us into trouble. I mean, we can go down that road. I don't even know what power I'd raise this to that would make any sense. But what we need to do to solve a problem like this is to recognize that this is a disguised quadratic. That is, it kind of looks like ax squared plus bx plus c equals 0. Well, how is that? Well, this is e to the 2x squared plus 4 e to the 2x minus 21 equals 0. So here e to the 2x is taking the place of x over here. Let's give it a different variable so we don't get it confused. Let's just say y equals e to the 2x. So this becomes y squared plus 4y minus 21 equals 0. Now this, of course, is something we have a handle on, right? We could either use the quadratic formula, or we can even try and factor this. Well, 21 looks like 7 and 3. The difference between 7 and 3 is 4. That looks good. So if I say plus 7 and minus 3, that's probably going to work. So this tells me that y could equal minus 7 or y could equal 3. But of course I'm not done. I don't really want to know y. I want to know x. So let's write these down. E to the 2x equals 3. And e to the 2x equals minus 7. Now, with the latter, we can stop right here, because no matter what I plug into x, I'm not going to get minus 7. We know that because the range on an exponential function like this is always y's are what? They're greater than 0. So we don't have to even follow this route. But this one's pretty straightforward. We can just find the log, the natural log of both sides. move our exponent over, and log of e is just 1. So this just becomes log of 3 over 2. I'm kind of glad you brought that up because I do have another example where one of the solutions doesn't quite work. But that's something you want to keep in mind. That's why I keep suggesting you have to check your answer. Okay. Let's look at that other problem I just described. This is probably the hardest such example we're going to run into. Let's take a look at log of x plus 1, log of x plus 2, plus log of x minus 1 equals 1. And this is log to the base 10. So, okay, I apply my logs. It's the log to the base 10 of x plus 2 times x minus 1. That equals 1. Now, once again, I want to write this as a exponential equation. So my base is 10, my exponent is 1, and here's my result. Okay, we have to do a little work here. X squared plus x, 2x minus x plus x minus 2 equals 10, or x squared plus x minus 12 equals 0. That looks like something I might factor. 4 and 3 equals, times 3 equals 12, and their difference is 1. So plus goes on the 4, minus goes on the 3. And I get the solutions x equals 3 and x equals minus 4. Okay, but we really have to check these. One of them looks a little suspicious. Plugging in 3, we get log to the base 10 of 5 plus log to the base 10 of 2 equals 1. That's just log to the base 10 of 10 equals 1. So that's good. Now let's try minus 4 and see what happens. Log to the base 10 of minus 4 plus 2 is minus 2, plus log to the base 10 of minus 4 minus 1 minus 5 equals 1. Now, you might be tempted to apply the law of logs here, log of 10, log to the base 10 of minus 2 plus log to the base 10 of minus 5. Log to the base 10 of minus 2 times minus 5? That's 10, that's 1. Well, that's why this worked out. But you can't do this. Because negative numbers are not in the domain of log functions. Just as they're not in the range of exponential functions. So, this solution here is out. That's why you have to check. Okay. Questions so far? We're going to look at something a little different. The next problem, let's take a look. What if x squared was equal to 2 log of x plus 2? Okay. Well, we're brave, so we're just going to forge forward, see if we can figure out anything about this. So let's divide both sides by 2. And then we see we've got a natural log function here and something over here. We can reverse this, right? We can write it as an exponential. The base here is e. The exponent is x squared over 2. And that equals x plus 2. Look at that and think, that doesn't really seem any closer to our answer, does it? So we've got an x over here, and we've got an x over here. And we really don't know what, we don't have any tools that let us combine these. I mean, we tried, but it didn't really help. And thinking about this, and we're going, wait a minute though. Let's just look at some values here for a second. For e to the x squared over 2 and x plus 2, let's look at 0. E to the 0, that's 1, and this is 2. Try 1. E to the 1 half, that's the square root of e. What's the square root of e? E is about 2.718. Square root is about 1.64. And this is 3. And then I just want to look at one more value, 2. So e to the 4 over 2 is e squared. That's about, about 7. And this is 4. Okay, so this goes 1, 1.6, 7. This goes 2, 3, 4. And these are smooth functions, right? They're continuous, even though you don't know what that means. It's like, as this function goes from 1 to 7, this function goes 2, 3, 4. Somewhere in the middle here, they're going to cross, right? If I would just, check a lot of smaller, numbers in between, somewhere in between, they're going to intersect. So I know there's a solution out there. I think it would help to actually graph this, take a look at what it actually looks like. Let's try that. Okay. I want to graph this one first. E to the x squared over 2. Let me just throw a few points out here. 0, that's 1. 1 is 1.6, and then 2, that's 1, 2, 3, 4, 5, 6. It's all the way up here already. So it's kind of looking like this. But of course it's x squared, right? That tells me something about the function right away. I mean, if I want to know what f of minus x is, right, that's e to the minus x. Let me write this properly. Minus x squared over 2. But the minuses drop. That's just e to the x squared over 2. What kind of function is that? We have a name for that. F of minus x equals f of x. It's an important concept. What is that? Important concept number 17 on the handout. Anyone care? Interesting. That's the first thing someone said in my other class too. No, it's not. There's no inverse. I mean, it has an inverse. We could find the inverse of that function. But no, this is. What is it? What is the feature of this function? Yes.
Even function?
Did you say an even function? Yeah, it's an even function. It's even. Very important concept. Well, if there's an even function, there must be, what's an odd function? F of x, f of minus x equals what? Yes?
Minus f of x.
Minus f of x. Okay. All right, now here's the clincher. What do we know about all even functions when we graph them? Okay, I'll put in some words. They are symmetric yes. Y-axis, yes. Like this is a mirror, whatever is over here is going to be over here. Okay, good. You need to know this. All right, so I just graphed this. Let me graph x plus 2. Y equals x plus 2, that's real easy. Got a y-intercept of 2. Has a slope of 1. It really looks like my original equation is going to have 2 values. I don't have any direct way to calculate them, but I'm pretty sure that, you know, I just picked a bunch of numbers. One of them seems between 1 and 2 here. This is negative. I don't know exactly where that is. It looks like I have 2 more answers. All right, so we're not gonna belabor this any further. We need some technology, right? Most of you have some technology. TI 83 calculator. These are not available on an exam, so those of you who are really good at logic will figure out I can't put one of these on an exam. But even so, you should know how to solve them. The really obvious direct way to do it with the TI is to just write this as a function, a single function, e x squared over 2 minus x plus 2, and see where this is 0. Because wherever this is 0, this will be the case. you do that, of course, you know, you plug in your function with your Y key, and then you say out 0, and then you have to, you know, you'll see the graph, and you know, either plug in some number like -1 or 1 here to tell it where to start. And if you do that, you will find out that there actually are two solutions, minus about 7117437 for 1.6007061. I mean, that's great at the push of the button. 2, 4, 6, 7 decimal points of accuracy. All right, that's nice. There might be a homework problem like that. Okay. There's one more problem I want to try. This is more of a practical problem. You're in business or finance, you might want to know how to do this, or you're in computer science and you have people you work for who are in business and finance, so you have to do work for, you might want to know how this is done. We're gonna avoid the complication here. You're going to invest at 5% per year, and we want to know how long at that rate it's going to take to double our money. Double or nothing, right? Well, if the investment goes sour, you know. Okay. The catch here is we want to know, based on compounding semi-annually or continuously. So two different problems. Okay, we need some equations here. So let's start with our equation for the future value of our investment. That's our initial value times 1 plus our interest rate, 0.05, divided by what? Semi-annually, it's twice a year. What do we want to divide by? 2. Yeah. 2. And then we have to raise this to, I guess, so each period now is 6 months. For a year, we need 2, right? 2 times the number of years. Okay, we're almost there. We don't really know what these are. We don't need to, because we're just going to divide by P0. And what did I say? You want to double your money. So what is the future value over the present going to be? And don't answer again, because it'll look like I'm cheating. Anybody? Okay, I'm going to try and state this really clearly. I have $5,000. In the future, I want to double my money, $10,000. What's the ratio of 10,000 to 5,000? What is 10,000 divided by 5,000? Okay, good. Now I understand. Everybody knows the answers. Nobody's talking today. All right. It's 2. I'm going to double my money. Okay. Well, even though this looks a little trickier for this moment, this is exactly the kind of problem we've been solving. It's a pretty simple version. Right? 1 plus 0.05 divided by 2 is 1.025 to the 2t equals 2. I want to find t, so what am I going to do? What can I do? Yes?
Log.
I can find the log of both sides. Let's pick a nice log so that if we have to use our calculator, it's going to work out, right? So let's take the log to the base 10 of 1.025 to 2t equals log to the base 10 of 2. And thank you. What do I do next? Let's get that hand down or I might call him. Look like you have the answer, Kenny, but you're afraid to answer.
Oh, no. Yeah.
No?
Yeah. Terrified.
What do I do here? Oh. I left this up for a purpose. Make sure everyone can see it. What do I want to do here? I'm going to move my exponent over, right? Somebody have a calculator handy? We can like plug these numbers in. I just have to solve for my t now, right? Someone want to do that for me?
14.035.
What was the first decimal?
0.
Okay, good. So it's going to take me 14 years to double my money. Compounding semi-annually. Right? But that's not the only problem here. Okay, one more. We want to know the same question, but compounded continuously. So that brings in our friend, the letter E, the number E, right? Our future value is going to be our current value times E to the T. Right? Oh, 0.05 t. Right. Well, again, Pf of t over P naught is equal to e to the 0.05 t. That, of course, is still equal to 2. How would I solve this equation? Natural log, sure. Natural log of e to the 0.05 t is the natural log of 2. The natural log of e to the 0.05 t, that has to be So if I take the natural log of 2 divided by 0.05, I will get t. Whoever was so kind to use the calculator last time, tell me what you end up with. I want to make sure I didn't do something really stupid along the way.
$13.86.
13.86. Okay, so compounding continuously is a little bit faster, not a lot, just a little bit. All right, that brings us to the end of logs. Yes? Why is this 2?
Yeah.
Because the question says, how long till we double our money? PF of t, that's the future value, divided by the current value. When we double it, that's equal to 2.
Okay.
Does that make sense? Triple our amount of money? 3.
Okay. It was because it said that it wanted us to double the value, not because of the doing things annually.
Well, we tried it both 5% semi-annually and then continuously. We could try other things too. We could try quarterly or daily, once a second. That would be very close to continuously. We can figure all those out. Okay, that brings us to the end of logs and exponential functions. That's where I'm drawing a line on the exam. We're going to go on this week and study trigonometric functions. Questions? No. Before we do, there's something that was kind of bothering me about the class. What was bothering me about it is it just seemed like we're learning a bunch of random things. I'm going to describe some of them. We learned a little bit about complex numbers. We learned about polynomials. We just spent some time with exponential functions. And log functions. Although I'm going to leave those off the list. They're just the inverse of our exponential functions. And we're going to go on and we're going to learn a little bit about trigonometric functions. Has anyone here not seen a sine or a cosine before? It's okay if you haven't. Okay, everyone has at least seen them. It just seems like this random group of things we're learning. We need them all in preparation for calculus. This is pre-calculus. But I thought it was kind of sad that, there's no connection between them. But yet, there really is a very close connection between all of them that it would be sad to miss out on. So I want to talk about that a little. Unfortunately, there are a few things that I'm going to show you that I'm just going to have to say, this is so. You're just going to have to take my word for it now. I can show you how, but then I have to teach you all calculus first, so that's not going to work. All right, and let's start off looking at exponential functions and polynomial functions. Polynomials. Polynomial functions are in one category of math, which we call algebraic functions. And exponential functions, along with trig functions, and another set of functions I might want to mention here. Has anyone here heard of hyperbolic? hyperbolic functions, hyperbolic sine or cosine, anyone? Put your hand, you know, up to your eyes, and I think you're saying yes, no. Okay, well, they're really easy, we're gonna cover them in about 60 seconds. These are called transcendental functions. And one of the features of a transcendental function is you cannot express the transcendental function as a finite polynomial function. You can get close. You can find a function, a polynomial function that gives you very close to the transcendental function, but not exactly. For your computer science people, you might want to think about that. How do we get e to the x on a computer? Well, computers, you know, don't raise things to powers very easily, but they do use, you know, deal with polynomials very nicely. You can calculate a polynomial very easily. Okay, so here's the rub though. You can express an exponential function like e to the x as an infinite series, an infinite polynomial. The way we would write this as an infinite sum is the sum for k equals 0 to infinity of x to the k over k factorial. Or to write out a few terms, this would be x to the 0 over 0 factorial plus x to the 1 over 1 factorial plus x squared over 2 factorial, and so forth. Now, just doing a reality check here. Do you really know what x to the 0 must be? X to the 0 be? 1. So I'm just going to call this 1 from now on. Does anyone know what 0 factorial is? Yeah, this is a tricky one. Just have to take my word for it. It's a good thing to define 0 factorial as 1. Life works out much better if you do that. Okay, let's just do a little sanity check here. According to this formula, what would e to the 0 be? Well, it's equal to 1 plus 0 plus 0 plus. Oh yeah, oh, that works. Okay, good. Take e to the 1. Be 1 plus 1 plus half plus a 6 plus a 24th plus a bunch of terms getting much smaller. Well, if I add these up, I'm going to get like 2.70 something. You can see where it's headed. It's headed towards E. Okay. Short little digression into hyperbolic functions. Hyperbolic functions are defined as follows. The hyperbolic sine of x is defined as e to the x minus e to the minus x over 2. And hyperbolic cosine of x is defined as e to the x plus e to the minus x over 2. A few brief comments. If you look, you can see really easily that hyperbolic cosine of x is an even function. I replace x with minus x, these two guys just reverse. Similarly, you can see that the sine of hyperbolic sine is an odd function, which kind of matches your trig functions, if you happen to know that. The cosine is an even function, the sine is an odd function. But let's figure out what these things are in terms of this expansion here. Well, this is, I'll just leave e to the x up and see what e to the minus x is. It's going to be 1. Well, 1x is going to be minus x over 1 factorial. 2x's, well, the minuses will cancel, so it'll be plus. And then you can see all the odd terms, they're going to switch. Now when I add these, like for the cosine function, what's going to happen? The odd terms are going to drop out. I'm going to get, well, I'm going to get these, just the even terms, but 2 of them. But since I divide by 2, I'm just going to get 1 set. So hyperbolic sine of x, hyperbolic cosine of x will just have this formula. It'll be 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial, and so forth. And hyperbolic sine is just going to be the odd terms, x over 1 minus x cubed over, plus x cubed over 3, plus x to the 5th over 5, and so forth. Okay. It's nice. We have these nice ways to describe these functions in terms of an infinite series of polynomials. I have enough time to bring this home. So now I have to just tell you something that you'll have to take my word for now. It turns out we have a very interesting set of expressions for our trig functions. The cosine of x looks very much like this. It's 1, but minus x squared over 2, plus x to the 4th over 4 factorial, minus x to the 6th over 6 factorial. And the sine of x is equal to x over 1 minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, minus so forth. In other words, these series look almost the same, except here every other term happens to be minus. All right. It's kind of cool. There's kind of a connection between the trig functions, the hyperbolic functions, these exponential functions, polynomial functions. The only thing I left out was, what does this have to do with complex numbers? Well, let's say I go back to this original equation and I say, well, what happens if I make x instead of x? I want to make x ix. Okay? I'm going to plug it into this formula. I'm going to get 1 plus ix over 1 factorial plus I squared over x squared over 2. Well, I squared, that's minus 1, right? All right, now plus I cubed, well, I cubed is minus I, right? So minus I x cubed over 3 factorial plus, what are we going to get next? Oh, I to the 4th, that's just 1. So we're back to x to the 4th over 4 factorial. Well, if I divide out the imaginary and the real here, I end up with, for the real, I end up 1 plus, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. This is just cosine of x. For the imaginary parts, if I take out the imaginary parts, I get x minus x cubed over 3 factorial plus x to the 5 factorial. The expansion for sine of x. And this tells me something really kind of amazing. E to the ix equals cosine of x plus I sine of x. This is a really important formula called Euler's formula. And one last thing. These x's are not in degrees, they're in radians. If you haven't heard of radians, don't worry, we're going to learn about them. The thing to know right now is that pi radians is 180 degrees. And if I plug in here, pi, e to the I pi, well, cosine of pi is minus 1. Sine of pi is 0. So I get this really famous Euler identity, e to the I pi equals -1, which excites a lot of people because you get all the big math numbers in it. You get e, you get I, you get pi. All right, that's really what I had to say today. Hope you're a little excited about trigonometry. And we will begin on Wednesday.